My name is Kevin Harms. I work at the Argonne Leadership Computing Facility. I've been working on DAOS for quite some time, and I'm also part of the governing board. I'm going to be presenting this work, which is for my colleague Kaushik Velusamy. He's on travel at the moment, and as well as Dennis B. from Inactive Labs. This is their work. I'm just trying to do my best presenting. Kaushik presented this work as well as at CUG, so if you're at CUG, you may have seen something similar. So we'll be talking about evaluating the PyDAOS work done by Dennis running on our system. All right, so in PyTorch, you have basically three modes of I/O that are provided through their abstraction. One is dataset loading, another set is model reading or model loading and model writing. And so the DAOS PyTorch can do all three of these, but the results I'm going to present are mainly from dataset loading, so I'll focus on that, but I'll mention the other two as well. And so first, just to take a look at what does it mean to use PyTorch and how does it work for this data loading and data writing. So we have the idea of you want to load some NumPy data. So we're going to create some class NPZ dataset. It's going to have some behavior. And then in order as we see here, there's a standard data loader. The data set is going to return it some items. So here it's loading some data using pickling and then creating a torch tensor and returning that. And so you see here the data loader then decides like how much data should be loaded and then does that and calls get item to get the items. Any of these type of data sets you can use directly with dfuse and or including the POSIX intercept library, but perhaps not at the best efficiency. And so what we'll show here is trying to optimize this using DAOS. So either the good or the bad, depending on your perspective, a data set, it's basically abstracting the IO model, the data model, and the data format all in one thing, rather than in some layered model. So what does, the PyDAOS.torch dataset implementation look like? So this dataset abstraction encapsulates all the I/O for data, and so this includes also this checkpointing part. But I'm going to focus on the dataset first. And so this dataset that gets passed to the data loader, which is just standard implementation inside PyTorch, so you don't overload the data loader, you just pass it a dataset. And there's essentially one abstraction, which is this get item or get items that can load multiple items at once. And all I/O is performed in this call. So the data set you pass, it will call, the data loader will call your get item call and then load the data. Then this last parameter you see here, transform function, this is where you would put your business logic. So this will do the other parts of the data stuff that's not loading, the DAOS data set just handles loading of talking to DAOS, right? Then you get back a binary set of data. What do you do with it? And that's what this transform function is provided for. So to basically invoke this, you can import this pydaos.torch.dataset. Here's an example where it's been renamed as DAOS dataset, and then you pass in the pool, the container, and then your transform function. And so this is a shim layer that's in Python that then calls the DFS API. And you can find this code in the DAOS tree. So here's an example of how you would look like in code. If you've seen PyTorch code before, hopefully this looks similar. You again here, so you include this PyDAOS torch implementation as the DAOS dataset, and then you call the constructor. So you're going to give it your pool, your container, and then some transform function. And sort of similarly as the first example I showed you with the NumPy dataset, what you're going to be passed is some raw bytes, and then you're going to get, so now you need to do something with those, and then your transform function again is going to do the NumPy load from the stream, and then return the data. So in your code, if you're using an existing data set, you'll need to adapt it to put your business logic in the transform function and then use this data set implementation. So then this gets just passed into the data loader. You can also use it for this model loading and saving. And so here this is a little bit more one-to-one. You just create this checkpoint object, and then you just pass it into Torch save or into Torch load. So this is a simpler, straightforward change. This using the data set is a little bit more complex. So then, and as an example, we're using, or we're emulating this UNet 3D data. So there's an existing data set you can go out there and get called UNet 3D. It's this type of data set where you have a structure of images that not just in 2D, but in 3D. So that's a stack of images, and you can use this model to interpret find objects, not just within a single image, but within the stack of images. So it's moving around. And so this might be used in MRI or CTs where you have a stack of images, or in a self-driving car where you're trying to find the distance the object is away. So this is a model and a set of data. And so we're using that as the example that I'm going to demonstrate here. So the next part is using this deep learning IO benchmark called DLIO. And so rather than me trying to summarize it, here's the text from the README. But the idea is this is IO benchmark where it supports different data loaders, formats, data sets from different types of deep learning systems. And so we're going to use this for loading this UNet 3D example data set via PyTorch. The upside for us is that there's no actual training being executed, so you don't need a GPU to run DLIO. You just use CPU only node, or just use the CPU, and you don't have to wait for the training to execute. So you can just evaluate the IO portion of the code of what you will see in PyTorch without needing to run your entire training stack. So the other thing is that because this is trying to emulate how data is loaded inside PyTorch while it's running, it's not to generate peak IO bandwidth. So DLIO is not going to saturate your IO system unless you configure it to do so, but that's not its general purpose. So the idea is to model what the system will see when it's running under PyTorch. And you can get this, this benchmark is also open source. So we're going to use DLIO with this UNet 3D data example to run the test. So then you need to configure DLIO, and then the configuration you choose is, the configuration that's like what represents the system that you want to run on. So for example, if we want to run a batch size of 7, that's what we selected here. Using a batch size of 1 is like a very interactive type thing, and then larger batch sizes are bulk processing. So like maybe bulk image processing that doesn't need to happen in real time might have a much larger batch size. The batch size, obviously influence your IO that you need to load, but also how your training executes. And so we're using Aurora for this. So the GPUs per node, we have 6 GPUs, but each GPU has 2 tiles. So we'll use essentially 12 GPUs. It'll be 12 instances of the kernel. Here, one sample is in a single file. So to load a sample is loading the entire contents of one file. And this benchmark set up to run for 100 steps. But on each step, we're going to load a subset of the data. So here, for each training epoch, we'll load 7 times 12 times the file size here, times 1. So for 8 nodes, that gives you about 90 gigabytes that are loaded for each step. And over the course, you can see for like 8 nodes, over the course of the entire 100 steps, you would load almost 9 terabytes. So this is you configure this to match your training or inference setup. So here is the results when we use the intercept library. So this is using the standard that data set, just using dfuse plus the pill for DFS. You can see here's our performance. If we use this native loader, we're getting almost 2x in performance improvement. And so it's mostly here due to efficiency. So if we look at this, we have about 75 gigabytes a second from 8 nodes. And if you recall from my slide, I said we have about a 90 gigabytes of data that we're loading on each step. So this load time is about 1 second. So we're just getting much better efficiency using DFS, bypassing all of the sort of interpretation layer, a layer of POSIX, and just going to defuse directly. And so right now, we only have limited scaling results because our Kaushik was away on travel, and then when he came back, our system is um, offline to do some maintenance on its cooling loop. So hope to run this to larger scales at a later date. But I'd like to thank the HPE team for helping assist with porting this, the current work back to 2.6 so we could do some testing. And of course, Dennis for his implementation of PyTorch. Any questions on how to use this PyTorch data loader?
So if you would increase the data set size, your expectation is that the intercepted approach over diffuse and the native approach would be more similar.
Yeah, if you started to sort of merge toward a bandwidth bound, my guess is yes, you will see
Hmm.
less difference between the two. But because here, like we're significantly under the maximum throughput of these nodes, the efficiency is where we're gaining.
Hmm.